Hello everyone, I'm happy to be back. Now we are going to talk about the most exciting part of this paper, at least from my perspective, which is the model. So let me not waste your time more and start talking about the model. Before that, just to make sure that we get the notation absolutely right and we are on the same page, let me remind you of this kidney exchange motivating example. So this guy here is a patient who needs a kidney and his sister is willing to donate him a kidney, but it turns out to be the case that they are blood type incompatible. This woman here also is a patient who needs a kidney. Her brother is willing to donate her kidney, but it turns out to be the case that they are blood type compatible. And it turns out to be the case that the donor of this pair can donate a kidney to the patient of that pair, and the donor of this pair can donate a kidney to the patient of the other pair, so they can have a kidney exchange. And this is how I'm going to show this phenomenon on a graph. So each circle in this graph, which I'm going to call a node, is going to represent a patient-donor pair. Okay, so it's an important notation that each circle here, which I'm going to call nodes or agents, is going to represent someone who is coming to a barter market. They have something that they want to exchange, and each link in this graph, these lines that you see, is going to show the possibility of a kidney exchange. So when I have a link between two nodes, it means these two nodes are compatible, i.e. they can have a kidney exchange. Okay, now with this notation in hand, it's time for us to go and actually talk about the model. Now, this model is probably one of the most natural ways you can extend the static idea of Erdős and Rainey, for those of you who know random graph theory, to a dynamic environment. It's quite simple, as you will see, and in fact, this slide is everything about the model. So let's go through these points one by one. So agents arrive to this market according to a Poisson rate M. So it's a continuous time model, and in expectation, M new agents come to the market. And for any two nodes or any two agents that you get in this market, there is a probability P that they are compatible, that there is a link between them. So agents come to the market, and then there is a probability P for any new agent to have an acceptable transaction to the previous agents of the market. And also for agents who are currently in the market, when a new agent comes, they have a probability P to be compatible with them. Now, this is how agents arrive, this is how agent forms compatibilities. Now, how agents depart, it's also quite simple. So each agent gets critical with a Poisson rate 1. So this is just a normalization factor. Each agent lives in the market in expectation for one period, but there is an exponential clock that ticks with rate 1. Whenever that clock ticks, that agent becomes critical, and that's the last point in time for the planner to match that agent. Now, this is a very stylized way for me to model the fact that I have short horizon but accurate information about agents' departure times. In the benchmark case of the paper that we are going to study together soon, I'm going to assume that the planner observes agents who are critical, who are about to depart, exactly at the moment that they are critical, but then I'm going to actually relax this assumption in both ways. What if the planner observes critical agents far ahead of time? What if the planner does not observe agents who are critical? And we will see the implications of this piece of information in designing optimal allocation mechanisms. But for now, let's stick to this assumption. Agents become critical, the planner observes, and that's the last point in time that the planner can match them. Now, agents depart naturally in one of the following two ways. Either they get matched, or they get critical and perish. Now, in order for me to make sure that you understand the model completely, let me show you an illustration of the model. So this rectangle here is my market. Agents arrive to this market continuously over time according to some Poisson process. There is a probability P to have an edge between any two agents, but it turns out to be the case that only these two agents actually have an acceptable transaction, or they are compatible, there's a link between them. Now, other agents come, they form these links, they form these compatibilities, and then I get the signal that this agent here is critical. Well, the planner cannot match that agent because this agent does not have any links. The agent is not compatible to anyone. So she is gonna leave the market unmatched. Other agents arrive, they form these links. I get the news that this agent here is now critical. In principle, the planner can match that agent to someone. Suppose the planner decides to match this agent to the agent on the top. What's going to happen is that they are going to get matched together. Their need is satisfied. For example, they are going to have a kidney exchange. They leave the market. And the point is that when these two agents leave the market, all the links connected to them will disappear from the network because they are not there anymore. So this is how the system evolves. Now, this model that I described for you basically has two key parameters, M and P, the arrival rate of agents and the probability that any two random agents have a link. Now, this one is also a parameter, but it's a normalization factor. So the key two parameters are M and P. Now, let's do a thought experiment. Suppose the planner does not match anyone. Then what will happen? Well, if the planner does not match anyone, then I claim that the expected number of agents in the market is going to be M. Why? Because the arrival rate of agents to the market is M, and each agent perishes with rate 1. So in order for the conservation of flow to hold, in order for the arrival rate to be equal to the departure rate, I need to have M agents in the market, so that when each one of them is leaving the market with rate 1, the total departure rate of the system is M. As a result, I need to have M agents in the market in expectation. Now, if a new agent comes to the market with M other agents being there, how many expected links that agent is going to have upon arrival? Well, with each one of them, there is a probability P, there are M of them, so this agent is going to have M times P expected links. Now, why I told you this story? Because now I'm going to make your world simple and define a new parameter called D, which is just M times P. And this parameter is basically a proxy for the average degree of the agents in my market, it's a proxy for the network sparsity in the system. If you increase M, if the arrival rate of agents increases, or if you increase P, i.e. agents are more likely to have links, you are basically increasing the average degree of the agents in their lifetime. And this is going to be a very useful parameter for us to work with. Basically, all the results of the paper are going to be stated as functions of D. Okay, now we are set with the model. I told you how the model works, how agents arrive, stay, and depart. Now actually it's time for us to go and talk about matching, and that's what exactly I'm going to do in the next video.